Hello there, we are working on section 1.15. Now, while the notes look kind of long, I think it'll actually go fairly quickly. There's just a lot of pictures that we're going to look at, a lot of graphs we're going to look at. So, first activity says to consider the following functions and graph it on your TI calculator. And the function is 3x squared over x squared plus 1. And for convenience, a table of values for the given function would yield the following. So it says fill in the blanks below. As x heads to infinity, my function would be doing what? Well, as x heads to infinity, so we can see here the x values are getting larger and larger, and I can see that my y value is getting larger, but then it starts tailing off 2.97, 2.9997, and then 3. I would say this function is going to settle in around a y value of 3. As I head to negative infinity, we can see our numbers getting larger and larger. And so the trend is that it too is settling in around 3. Therefore, we can say what pair of limit statements? Oh, so trying to make two limit statements. Let's say the limit as x heads to infinity of the function, which is f of x, equals 3. We can also say the limit as x heads to negative infinity of f of x equals 3 as well. Limits at infinity. The concept of limits as x approaches infinity means the following. What happens to happens to y as x gets infinitely large? We're interested in what's happening to the y value as the curve gets farther and farther and farther to the right. In other words, we are saying, as x tends to infinity. So that gives us this limit as x heads to infinity, and it informs us about the end behavior of our function. And we're looking at end behavior at the right side of our graph. And then likewise, as we head to negative infinity, we're getting end behavior on the left side of our graph. So examples 1 through 5, looking at the pictures for each graph of f of x, find the given limit. As we head to negative infinity, so as x gets larger and larger, what is happening to our y value? Well, just follow the curve, and I can see that as we head away from the y-axis, our y value is getting very, very large in a positive direction. And then on this side, we are also headed to positive infinity. So as we head to the right, we are headed upwards, which would be positive infinity. As I head to the left on my graph, it would appear that we are headed to infinity once again. As we head to the right on our graph, I would have to say we're headed to negative infinity. So no horizontal asymptotes on either of these because the end behavior is such that it just keeps going and going and going. It's not settling in on a value, such as in this example. Oh, what example is this? It's not labeled. In this example A here, A and B, as I head to negative infinity, so as I move left on my graph, it appears that we are around 4. As I head to the right on my graph, it appears that we're at a height of -2. The y value is -2. These will be horizontal asymptotes on our graph. As we head to negative infinity here, well, this one's doing a bit of waving, but it does seem to be damping down. It's getting less and less erratic, and I would have to say as I head out even further, it's going to stay consistent and come in around 1. As I head to the right, we have lots of oscillation, but it is settling down, and I would have to say as I get out to infinity, I would say we have a horizontal asymptote at 0. Example number 5, as I head to negative infinity, well, this one does not show me any trend of settling. I would just say it's DNE because I honestly don't know whether it's going to be positive infinity or negative infinity. So I'm just going to go DNE on that one. As we head to infinity, this one does appear like it would just keep going up and up. I think you would be safe in saying infinity. However, it wouldn't be incorrect also just to say DNE. The limit at infinity theorem. If r is a rational number, then the limit as x approaches infinity of 1 over x raised to the r equals 0. And because they restricted r to be positive, I know that if r were to be negative, it would change its position, right? If we get a negative exponent that's saying the same as x over 1, it moves position. So we don't want that happening, so they are restricting r to be strictly positive, and therefore it will be locked in the denominator. And if I have x to the r, and x is getting very, very large, then this is going to tend to 0. Because if x gets large and is raised to a power, then this is going to be 1 over some big number, and 1 divided by big will give us 0. If I have negative infinity as x heads to negative infinity, it too will turn into 0. Evaluating a limit at infinity. So if I think about this one, I'd have 5 minus 2 over infinity, which is like saying 5 minus 2 over, extremely large. Well, this will go to 0. 2 over large is going to go to 0. That'll give me 5 minus 0. Looks like I have a limit of 5. If I head to infinity, these look like they are basically saying the same thing, right? And how do you analyze that? Infinity over infinity. Are they the same infinity? Well, the best way to do it, the most official way to do it, is to look at this as the limit as x goes to infinity of 2x minus 1. I'm going to give myself a little bit of room to write in a denominator there. And officially, what you want to do is come in and divide by the largest power of the denominator. So I would divide by x, and every single term is going to get divided by x. If I do that, and x is getting large, this will go to 1, this is going to 0, this is going to 0, and this is going to 2, because I have x over x canceling. So I get 2 minus 0 on the top and 1 minus 0 on the bottom, which gives me 2 over 1, which calculates to just 2. So that is the best way, as you select the highest degree in the denominator as your divisor. As your divisor. I think I missed an I there. As your divisor. Why would you choose it from the bottom? Because I do not want my denominator ever to go to 0. So if I choose it to be from the bottom, it is not going to go to 0 then, because I'm choosing the very highest degree in the bottom, and I'll always get at least 1 then as a number. Okay, a comparison of 3 rational functions. Let's find the limits of each of these, a, b, and c. And we are going to select highest degree. And I see that the highest degree is a 2. So I'm going to take every term and divide it by a power of x squared. So 2x divided by x squared plus 5 over x squared, 3x squared divided by x squared plus 1 divided by x squared. Now analyze each of those. 2x divided by x squared. X is getting large. Remember, we're on a limit function. So that's going to go to 0. This term's going to go to 0, giving us a 0 in our numerator. Here we talked about, we chose the largest degree, so those will cancel, giving us 1. 3 then times 1 will give us 3. 1 divided by x squared gives me 0. Add those together, I get 3. It appears to me that 0 is our limit. On this next one, x squared is our highest degree. So I'm going to have limit as x goes to infinity, 2x squared divided by x squared plus 5 over x squared. It's a lot of extra writing, but we understand why we're doing it. And let's analyze each of these. X squared over x squared, it appears that this particular one's going to 2. 5 divided by large is going to go to 0. That's going to give us a 2 on top. 3x squared over x squared, that's going to give me a 3 on the bottom, and this is going to 0. So this is going to 3. 3 plus 0 equals 3, and I get 2/3. Which just so happens to be the coefficients of the like terms in the numerator and the denominator where they were equal in degree. The last one, where am I going to put that work? The limit. Let's see if I can squeeze it in here. As x goes to infinity. Well, 3x squared is my largest degree. Every term's going to get divided then by an x squared. You write them down, I'll write them down. 3x squared over x squared plus 1 over x squared. Do your individual term-by-term analysis. The top left term, 2x cubed divided by x squared, that would leave me a 2x in the numerator. And if I let x go to infinity, this will go to infinity. The next term, 5 over x squared, goes to 0. 0 plus infinity is infinity. Let's see, this is going to 3 on the denominator, and the other one's going to 0, so we got a 3 in the denominator. Infinity divided by little old 3 would turn out to be infinity. Where am I going to put my answer? This turns out to be infinity. Notice that the degree of the numerator was higher than the degree of the denominator, and therefore it has more say in what the function's doing. In the very first one, the denominator had the higher power, so it is more persuasive. It's going to dominate that fraction and took the denominator to a much larger value than what the numerator was, and thus we saw that the limit went to 0. This can all be kind of simplified into 3 little guidelines, and you may have seen these in pre-calc. So it says if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. And that would be like in example, was it called 1 or A? See example A. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function turns out to be, well, this one turned out to be 2/3, which is just the coefficients, isn't it? It's the coefficients of those 2 terms. You know what I'm going to add in there? It's the ratio of the coefficients. That would sound a little bit better, I think. The ratio of. All right. And then if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function can either be positive or negative infinity. And those get a little tricky. You have to do a little more analysis, especially if you're headed to negative infinity, your limit. So as I approach infinity or negative infinity, there is an extra step of analysis going on to determine whether your outcome is positive or negative. All right. So let's do example 9. And I told you we were going to rock through these pretty quickly. So limit, as x goes to infinity, find each of the following limits. Well, this looks complicated. We have a square root. But what if I just had square root of x squared? Well, the square root of x squared turns out to be x, doesn't it? And that is a match for my numerator degree. So I think it's going to be the coefficients of the highest powers, which are equal in power. I am going to say that this has an outcome of 3 over square root of 2. But I want to show you how to show it mathematically rather than using those simple guidelines. So what we're going to do is in our denominator, we selected out our highest power, which is really a power of x. All right, now let's go with the limit as x goes to infinity, 3x minus 2 divided by, I'm going to show the square root of x squared. And then on the denominator, I've got the big square root. I've got 2x squared over an x squared plus a 1 over an x squared. And then it has the big square root outside of it. So it's really a square root of x squared on the bottoms. Now, analyze each one individually. So this will be 3x over x. That's going to go to 3. This is going to 0. This here is going to square root, almost wrote 1, square root of 2, and this is going to 0. So I do 3 minus 0 over square root 2 plus 0 in our square root gives me final answer of 3 over square root 2. And on top, it's going to be a positive. On bottom, it's a positive. So I'd have positive over positive. I just did that extra little step of analysis. All right, the next one. We do hit the same function, but they want us to analyze it from a negative infinity. So if I thought about 3 multiplying by negative, I would end up with negative 3 there. This would go to negative 3, would it? Would it not? Yes. And on the bottom, I've got the positive square root. Negative infinity is getting squared, so that would also be positive. So I'm going to end up with a positive number underneath the square root, which is a good thing because we do not work in imaginaries in AP Calc. So I would get an answer of negative square root 3. This is the tricky part. So watch that step right there. Sometimes that gets people. Next page. Horizontal asymptotes. So definition of a horizontal asymptote. The line y equals L, which we know is a horizontal line equation, is a horizontal asymptote of the graph f of x if, as we head to negative infinity, we get that value of L, or as I head to positive infinity, I get that number of L. This will be left end behavior as we head to negative infinity. And of course, this is going to be right end behavior. It gives us a quick way to analyze what our function is doing on the far reaches. Sorry about that. All right. Next. So it says determine the equation of the horizontal asymptote. Basically, what we got to do is find the limit. Whoops, not writing. The limit as x goes to infinity and the limit as x goes to negative infinity. For this one, I want her 4x plus 5 over 2x squared plus 1. I'm going to do the quick analysis from those guidelines of the three things, and I'm looking at the highest degree of the numerator compared to the highest degree of the denominator. I can see that this is going to go to 0. And if I put in positive infinity into both of those, I end up with positive numbers. It's going to 0. The other one, let's analyze the bottom. Once again, I'm looking at the highest degree. The other stuff doesn't really get or it really isn't impacting those lead terms because the lead terms are so much larger than the other terms. So I get 4x divided by 2x squared. Well, the 2x squared is going to dominate and get super large much faster than the top. That's going to drive this to 0. And negative infinity, this would be a negative number divided by a positive number, but the positive number is so large it's coming into 0, but from the underside of the function, but it's still, whoops, drew that backwards of what I wanted. It's still going to come into 0 as its horizontal asymptote. So we have a left and right horizontal asymptote that is the same in this case. Y equals 0 is our horizontal asymptote. For B, I noticed that the coefficients 4 over 2 are that x squared is over x squared. So I'm going to really focus in on the coefficient. Same degree, look at coefficients, right? It's the ratio of the coefficients. Get it spelled right there. So I know that the limit as x heads to infinity of 4x squared plus 5 over 2x squared plus 1 is going to be, well, the x squareds are going to cancel. I'm going to have the 4 over 2. We're headed to 2. And positive and negative infinity will be the same because of the squaring going on with the x. So of f of x, that will be 2. We have a horizontal asymptote at y equals 2. And C, I noticed that the degree of the numerator exceeds the degree of the denominator. I got a higher degree in the numerator, don't I? That means that it is going to dominate this function. And it's going to grow quickly, either to positive infinity or negative infinity. Now, I think we better analyze this one separate. So the limit as x goes to positive infinity of 4x cubed plus 5 over 2x squared plus 1 would be positive on top, positive on bottom. So I'm going to get a positive infinity going on. This is dominating. The numerator is dominating. There we go. Kept wanting to say denominator. All right, now, if we head to negative infinity, I'm just going to change this up. How does that change the picture? Well, the top, a negative getting cubed, will slip to a negative. The bottom, being squared, will still be positive. And the top being much larger in degree, well, not a lot larger, but enough larger that it's going to dominate, will take this to negative infinity. So there are no horizontal asymptotes in this one because the end behavior is going positive infinity, negative infinity. I'm going to cut this off right here and make another video. This is This is getting pretty long, so I'm going to stop this video right now and we'll go into a different one.